So the topic is constant rate of change, which we've sort of talked about already, except for rate of change. Rate of change is different than the ratios that we have talked about already. And that's kind of the key point here. Okay. So the page numbers here are either pages out of the 7th grade book or pages out of the 8th grade book. They don't mean anything to you guys. All right. So we're just going to talk through this stuff. So rate of change describes how one quantity changes with relation to the other. When we've previously worked on tables like this, we've always done the ratios of y divided by x, the actual numbers in the table. Those changes, okay, those ratios. That is not rate of change, okay, unless it's a proportional relationship, which we'll get to later. Rate of change is the ratios of how much each one changes in the table, okay? And we use this symbology here, this triangle thing, to signify the change in something. Does anyone know what this is? Who said that? Stephanie? What'd you say? It's a delta. Oh, yeah. This is a delta. It's a Greek letter D.
Okay, I've seen it before. I said actually what it was.
Yeah. Okay. So it's a Greek letter D, uppercase Greek letter D. A lowercase Greek letter D looks like this. Oops. Looks like this. It's kind of a weird squiggly.
It's a music note.
Yes, kind of. Okay.
It's half
But
of an 8.
yeah. But this is an uppercase D in the Greek alphabet, right? What other letter of the Greek alphabet do you all know and use?
Alpha.
Well, okay, but in math class,
Pi.
pi, thank you very much. Pi, that's a Greek letter P.
I want
Okay.
pi. Well, that's just not fair.
What's not fair?
Oh, pi.
Yeah. So,
You're like, yeah, whatever.
I don't know what he's talking about.
Who knows?
Delta. So delta means the change in something, okay? It's used in science all the time. You get the chemistry class in high school, you'll use delta all the time. But delta means the change in something, okay? We talked about this before when we were talking about these tables, that you always have to identify there's an input value and an output value in these tables. The input value is represented by x typically. You can use other variables too. But x, the input or independent variable of these two things, and y is the output variable. And again, if it doesn't tell you what's x and y, the x is the values that you would choose, and the y are values that you would calculate typically. Okay, sometimes it's obvious what's the input and what's the output, because here, you're picking a number of lines of code and how much this person makes money, that's the one you would calculate. So the lines of code is the input, the money is the output. And what you're looking for is the change in both of these things. Delta x is the change in x value, so it goes up by 50. And the related change in the y value, okay, when x goes up by 50, the y value goes up by 1,000. He writes 50 more lines of code. The amount of money that he makes goes up by 1,000. He writes 50 more writes 50 more lines of code, and the amount of money she makes goes up by 1,000. Okay, so this is calculating the change from one step in the table to the next. If you can't do these in your head, it's a subtraction, right? It's 100 minus 50, 150 minus 100. Typically, they're ones you can easily do in your head.
Wait, customers? What does that mean? Who's buying one?
Who buys computer programming code? Anybody who does anything that needs a computer. Somebody has to write the programming for it,
Oh.
right? So she's a
What is she
programmer.
writing?
She's writing computer code.
So 50 lines of code gives you 1,000.
That's how much she charges to write the code. So how much is it per line of code? That's the rate of change.
That's like so 200.
Okay, so the change in y here, it goes up 1,000 every time. The change in dollars, every time the change in lines goes up by 50, which means that her rate of change here in this situation is $20 per line. It's a unit rate. Okay, rate of change is what?
50 million lines of code.
Just saying, 50 lines would go by in an instant. This would cost like billions of dollars.
Yes, that's true.
Million.
Because this ratio is always the same, $1,000 for 50 lines of code, it is a constant rate of change. The change in Y divided by the change in X is always the same. So no, don't say that. $20 per line. That's the constant rate of change. Okay? All right. So from a table, you should be able to find the constant rate of change. So this example, which was completed in this book, shows the amount of money that a booster club makes when they wash cars. Okay?
What's a booster
A
club?
booster club is like a group of parents that support, like there's music boosters at the high school and there's athletic boosters at the high school, right? So boosters are usually parents that support some kind of student or child
And then like
organization.
during concerts, there'll be like boosters.
Actually, that's not true. There's boosters, like there's boosters for the opera and boosters for, it's people that support some kind of program. Okay, so the amount of money goes up $40 every time the amount of cars goes up by 5. So the constant rate of change here is 40 divided by 5, which is $8 per car. That's the rate of change. Constant rate of change is a unit rate, okay? And, what does it mean? Well, it means for every car, you get another $8.
Oh,
Right.
I understand.
Okay? So this table shows how far a plane travels while it is flying. What is the rate of change in miles per minute? What is the speed? Is the speed basically miles per minute for this plane? So I'm going to have to calculate the change. First off, I got to decide which is X and which is Y. And for speed, time is always the X.
Why is time always that?
Because rates are something's per minute, something's per day, something's per hour, something's per, right? So there are exceptions, but almost always when there's something changing over time, time is the X, the independent variable, okay? And distance is the Y. And so what we're going to find is the change in X and the change in Y. And this is kind of how you set these tables up. So the minutes goes up by 30 and the distance goes up by, conveniently enough, 290 to 5. It's actually 290, okay? 580 minus 290. It's maybe easier to see on this one, right? So, and these problems you're going to see now, they're all going to be constant rates of change. Later on,
Why'd you write plus 30 down?
the plus 290 is what I meant to write. Yeah, right? So what is the rate of change for this? Yes, Maggie?
I'm very lost. Like, what are we even doing?
Finding the rate of
But
change
that's what we didn't.
for this. Nope. What we did before was the ratio of this to this. Now, why are they the same? Because all these problems that we are looking at here are proportional.
Yes, but why are we?
If it is a proportional relationship, the rate of change is going to be the same as the constant of proportionality, which is this divided by this, the y divided by x, not the change in y divided by the change in x. So maybe it's better to just zip through this stuff and get to what happens when it's different, right? When it's not, when it doesn't look as simple as this,
Please do that.
okay?
Because you just confused me.
All right, so here's one. Okay, this one is different. Hero Comics prints on recycled paper, and the table shows how many pounds they have recycled. Now this one's proportional also, but at least it doesn't start at 1 and it's not quite as easy to see. Okay. One thing that people will look at is this pattern here, 3, 5, 6, 7, 12. These don't go up by the same amount every time. Some people will think that means that this can't be a constant rate of change. That's wrong, because you're not looking at the actual how much these go up. It's the change in X and the change in Y, okay? So what I'm needing to find here is what does this go, how much does this change on the table from 36 to 60? That's 24. 60 minus 36. for an increase over here of 2 months. Then the next step in the table, for a 1 month increase over here, how much does it go up by?
12.
12.
So you're saying like if it was +0 at one point, there's no change.
It won't be +0, but not that there's no change. That it's not constant is what we're gonna find in some cases, okay? And then here, this last one, it goes up by 5. What are you doing, Pen? Oh, I understand what you're doing. Up by 5 months, and the increase over here is from 84 to 144, 60, okay? So now, is this a constant rate of change? Yes, 24 divided by 2, 12 divided by 1, 12 divided, it's always going up 12 pounds every month. Go ahead.
I'm still.
You don't understand what we're getting to.
No.
I understand.
How do you write this down and like what? Yeah.
Yep, we haven't really asked any problems yet, other than what is the constant rate of change for this problem?
What does that even mean? Like what is constant rate of change?
It's how much it's the rate of something, the rate that something is changing. Okay, it'll come more clear as we get to do more problems. Graphing this, let's look at the next step here. So graphing this relationship, if I were to graph these points, 336, 560, 672, if I graph all these, you might recognize that the pattern of this graph, what shape would you say these dots come out in? A straight line, okay? A straight line. Okay, and it probably starts at the origin, which means that what kind of relationship is this? It is a proportional relationship, a straight line that goes through the origin. Okay?
So are you graphing
This and this. Not the changes, okay, just the actual values. That's what's graphed on here, the number of months and the number of pounds recycled. Okay? Why is this graph a linear graph? Why is this called a linear graph, Lucas? Because the graph is a straight line, okay? This is a linear relationship. The points make a straight line. It is a constant rate of change, okay? So between 2 points on this graph, you could also do the same thing we did over here and find that it changes 24 pounds over 2 days, or that the constant rate of change is 12 pounds per day. What does it say here? Okay, 12 pounds per day. Yes, Lucas? Correct, there's no title on the graph. That's why there's a Mr. Yuck. The books don't put titles on their graphs ever. Very bad.
That's just trash.
Yeah, okay. All right, so this is a linear relationship.
How do you speak recycle?
She's thinking. She's thinking. It should be a cloud.
That is a speech bubble.
I know it should be a cloud because she's thinking recycling. I think.
Oh, you're thinking that
I
you're
can
thinking
speak
recycling.
Lucas. I speak
Or
for
maybe I'm
recycling.
thinking that you're thinking that she's thinking about recycling.
All right. So what we're really getting to here is we talked about proportional relationships in this unit already, but and every proportional relationship is also a linear relationship. But there are relationships that are linear that are not proportional. We haven't gotten to that yet, but that's where we're getting to. A linear relationship is a relationship between two quantities that has a constant rate of change. Okay? So here, the rate of change here is that it goes up 2 songs every minute, the downloads that this person is doing, 2 songs every minute. Okay? If we graphed it on the previous page, the graph of all this would be a straight line. Okay? Goes up 2 songs every minute. That's why it is called a linear relationship, because the graph is a straight line. The rate of change is constant for a linear relationship. The rate of change is constant. And if it's proportional, goes through 0, 0, right? Then the ratio, the rate of change is going to be the same as the constant of proportionality, which is dividing 4 divided by 2, 6 divided by 3, 8 divided by 4. Okay, this is a proportional relationship. Now, part of the problem, what Maggie's having trouble with here is these things all seem like they're all the same number, right? Like 2 divided by 1, and these all come out to 2 over 1. And in proportional relationships, that is true. They always come out to be the same. It's in a non-proportional relationship that this falls apart. This is a non-proportional relationship. Okay? But it is a constant rate of change. Every 3 months in this bank account, the amount goes down by $30. Okay? Every 3 months, the amount goes down by $30. Does this have a constant rate of change? Yes. It's always minus 30 divided by 3, right? Which is negative $10 per month, right? Or negative $10 per transaction, rather. Sorry. So every transaction in this bank account, it loses $10. It is a constant rate of change. It is a linear relationship. Is this a proportional relationship? No. It's not proportional because this graph is not going to go through the origin. Okay, it actually goes down like this. And also, it's not proportional because the ratio y divided by x, not the changes, but the actual y and x values, these ratios are not the same. They're not constant, which is what we did 2 weeks ago. Not proportional, but linear. Okay? What is the graph of this relationship going to look like? It's going to be a straight line, but it's not going to go through the origin. So it's a linear relationship, but it is not proportional. Constant rate of change means the graph is going to be a straight line. And that means it is a linear relationship. One thing to be careful about. Don't look at the pattern. We already talked about this in that other table. Don't look at the pattern. The book keeps doing everything. It's like, okay, it goes up 3, up 3, up 3. And you think, since these are all plus 3, it must be a constant rate of change. Has nothing to do with that. It's the change. So what I do is I sometimes delete one of the rows out of the table. I'll say, okay, now look at it. If this row wasn't here, is this still a constant rate of change? The change in x, right? This goes up by 3. And then it goes up by 6. Hey, those aren't the same. It's not a constant rate of change, some people would say. No, we don't care about what these two go up. It's the ratio of the change in y.
I'm literally so confused right now. Oh, I understand.
The change in y divided by the change in x is what has to be the same. That ratio of the change in y divided by the change in x, that is the rate of change. The ratio of change in y divided by change in x. If that ratio is constant, that relationship has a constant rate of change and it is linear, which means that its graph would be a straight line. Maggie.
If you take out a row, it's obviously going to be different because you can't.
It's not different. What's different, the only thing I'm pointing out is over here, you see how this goes plus 3, plus 3, plus 3? There are some people who would look only at those numbers and say because they're all the same, that this is a constant rate of change. And that's a mistake. It's not this pattern that you are looking at. It's the ratio of the change in this number divided by the change in this number. That's the important thing to look at. Because it's a rate. Rates are always division. Comparison of two quantities by division. Rate, ratios, that's the rate.
So if not all the bars, when you divide the y by the x, if they're not all the same, then it's not a constant rate of change.
Correct. And if you graphed it, it wouldn't be a straight line. Right? If the rate of change is different, it's not a linear relationship. And we'll get to those examples in the next class. Okay? In fact, this, I'm not going to assign any problems on this stuff right now either. Well, in cohort time, you will. Okay? So the question is, do these problems have constant rate of change? Which is one of the things that you're gonna, that's what you'll be asked to do in these problems. Is this a constant rate of change? Okay, so it's looking at the change in Y, the change in output, divided by the change in the input.
No. So it's no.
So number one, the time goes up by 5 and the temperature goes down by 5. So that ratio is -1 degree per minute. That's the rate of change for the first step in the table. Then this goes up by 10 and the temperature goes down by 8. What? From 90 to 82 -8. I had to delete this because it was all the same over here, which makes it too easy to see the answer without knowing the math.
Oh, was it 5, 10, 15, 20?
Yeah, 5, 10, 15, 20, 95, 90, and then something else and not a pattern. Don't look at the pattern. The pattern is not the math. This is the math.
The pattern doesn't matter.
Right.
Wait, but if it's like, so say you have like 5 on this side, and you have like 5, 5, 5, 7, 6, 5, you could just automatically tell that.
Correct. You could just look at it and answer without knowing the math, which is why I don't like problems that are that easy. If it was that, you could answer it that way, okay? But this one, you can't notice exactly, but now you see, okay, well, this changes twice as much and this changes not twice as much. That's in your head calculating that these two numbers are not the same. The rate is not the same. So the answer to this one is no. No, this does not have a constant rate of change, this problem. It is not linear. If I were to graph this, relationship, it would not be a straight line.